Good morning, all. Uh, in the last talk, you heard about parallel architecture. What I'm going to do is that I'm going to give a quick overview of planning, what, and then give a quick introduction to OpenMP. Right? Yeah. That's essentially the plan. What I want to do is that I want to actually run through my slides first for about 15 minutes or so, and then leave the last 10 minutes for questions and answers. But if you do have an urgent question or something that you think is very important to understand something, please feel free to ask a few questions. Okay. So as I said, the agenda is to give some basic introductions, talk about steps involved in parallelization, and do a very quick introduction to that. Right? All right. So that's the overview. In the last lecture, you saw about different kinds of parallel architectures, what are called shared memory architectures, right? Which have the notion of space being shared, right? More than one processor or more than one node. Right? There are two different varieties here, what is called the centralized shared memory and distributed shared memory. Essentially, says one has the notion of locality that needs to be taken care of. The other one, the accesses are the same cost, so the locality is not to be worried about. The second kind of architecture is what are called the distributed memory architectures, which do not provide this notion of a shared memory. That means that different processors or different nodes, so it has so in the case of the distributed memory architectures, processors have their own address space, or they have no notion of what is called a shared memory. Right? Therefore, they cannot directly access the memory of whether processors or whether node. Therefore, they need to communicate only by means of messages. So these are also called message passing architecture. There are a lot of clusters that you see are essentially message passing. The third class of architectures are what we call as the data architecture. In the olden days, these were array processors or simply machines, and also what are called vector machines. These are different classes of machines. There are some subtle differences between them. We group all of them as data parallel. In the modern context, accelerators like GPUs also fit into the same category as data parallel architectures. We will talk about each of these architectures and what are the different programming models could be used for these architectures. The programming model essentially says how the programmer specifies the applications, right, for these architectures. The programmer also has to specify the necessary synchronization and communication between these processes. How do these processes interact with each other? So that also needs to be specified by the programmer. Therefore, should be for the programming model. Broadly, we will talk about three different programming models. One called the shared address-based programming model, which explicitly uses the notion of the shared memory. Right? The shared memory can be provided by hardware, as was discussed in the last lecture. Shared memory abstraction can be provided by hardware, or it can be provided by the software, which we have not discussed. It's a little bit more expensive in terms of execution time. Therefore, it may not be worth talking about it exactly. Right? And in that shared address space, you kind of program your application and you use, interfaces like OpenMP, OpenMP, which one. Okay. The other class of programming model is what are called message passing programming model or distributed memory programming model, in which there is no notion of session. Where different processes operate on their own set of variables and data. They communicate with each other by means of sensory messages. They also do other synchronization. So those languages or those interfaces are called message passing interface. Right? You will hear more about message passing interface in the next lecture by Professor Ishwar. The third class of model that we are going to talk about is what are called the models for data parallel languages, right? Which again, languages like CUDA and OpenCL fit into this class. And these are typically for accelerators or data parallel with GPUs. Although each one of these programming models is specifically suited for one or the other architecture, it's quite possible to take your MPI program and run it on a shared memory architecture, provided there is support. Right? Similarly, you can take your OpenMP program and possibly run it on a message passing architecture. There is support for this shared memory abstraction from software. Or take your OpenMP program, convert it in some way, and be able to run it on GPUs. Today, OpenMP 4.5 and 5.0 support constructs for running it on architectures like G. And even though we kind of classified these programming models and architectures in separate things like shared memory architecture, distributed memory architecture, so look at any of today's performance computing system. It's not just one kind, right? You have the notion of a cluster with multiple nodes, and within each cluster, right, you have multiple processors or multiple circuits which share some memory. Therefore, they also have shared memory abstractions in them. And then you can also see that within each node, you have the notion of a GPU being passed through. So essentially, if you see today's HPC architecture, high-end parallel computing systems, they do have distributed memory, they do have shared memory in them, and they do have data parallel architectures in them. So it's not easy to think, okay, this is a separate bin, that's a separate bin, they don't talk to each other. Similarly, these programming models that you talk about, they also today you have OpenMP plus something, or today you have MP8 plus CUDA, right, and so on and so forth. So it's a combination of things. So what you're going to see today is some introduction to OpenMP and CUDA, but we're going to deal with them in an isolated fashion. But then later on, when you run your large applications, you may be using MP8 plus CUDA or MP8 plus some form of shared address space, so on and so forth, if you want to extract form and so on. Okay. Now, before we go into the parallelization stuff, I just wanted to quickly talk about a thing called speedup. Speedup is important because when you take your application and you parallelize it, you want to see the benefits of parallelization. Let's say if you are running it on n processors, right, then you want your execution time to reduce somewhat proportionally, right? So the thing we are going to define it as speedup is defined as the ratio of execution time on a unit processor. That's execution time on n processor. And you expect this value to be closer to 1, right? And if it is closer to 1, your efficiency is 1. And most of the cases it will be below 1. Right? You will have a speedup which is less than, right? Yeah. And there are some cases where you can actually have a superlinear speedup also, but we will not talk about that here. Right? Now, why do you get this performance lower than here? Let's look at that particular. It was actually described by this law called the Amdahl's law. It's important to know this because when you parallelize your code, right, you're always focusing on the part of the program which can be parallelized, right? And then say that some part of the program is not going to be parallelized. And that's going to run on the sequential process, right? And that's going to run on a single process. Let's say if 20% of your program is sequential, then no matter how many processors you have, no matter how big a system you have, 20% of the time is going to remain as it is. Right? Assume that your program takes 100 seconds. 20 seconds is taken by the sequential part, and let's say that you can somehow reduce the remaining part of your time by using very, very large number of processors. Still, you are going to get only a speedup of 5, right? Therefore, the speedup that you can get is essentially limited by the part of the program which is sequential. Therefore, when you parallelize your program, you have to focus more and more and then try to reduce this steps to as small a value as possible. So, if you say that you want to run your application on, let's say, 1,004 processors, right, and you want to get a speed up closer to 5,000, and the sequential part should be significantly lower than 1 by 5. Otherwise, you can't get anywhere. Right? That's the whole idea, and that's the reason why I wanted to bring it over here. Okay. Now, let's just give an example for this Amdahl's law. So, assume that I do a computation on an n by n grid. Okay. And then I want to accumulate all of these values into a single value. Right? So, the sequential algorithm will basically go through all of these n squared elements and then slowly accumulate them one by one. So, it will take another n squared. So, your serial time is 2n. It's very simple. Right? Now, if you want to parallelize, what can we do? can certainly parallelize this because doing some computations on these elements as long as independent of each other, they can be done, right? And if you have p processors, then I can actually do it in m squared by p time. But accumulating all of these values, there is some synchronization required. So shared variable that I'm going to. I have to add to that. And I will explain to you why this synchronization is required. It has to be done somewhat sequentially. Otherwise, you're not going to get the correct answer. So if I use this kind of a parallelism, which I call as the naive parallel method, then the first part can be parallelized using the processors, and I can do it in m squared by time. The second part still has to be done sequentially. And since this is taking more than half the time, we're not going to get any speed up before then. Right? Whereas if I think a little bit more about the sequential part, and then see how I can speed this up. One way I can do is that if I have p processors, then in each processor I will accumulate what is called the local sum of these m squared by t elements. For every processor has now m squared by t elements, I can accumulate that sum without interacting with any of the other processors. Right? Then I can do it in m squared by t because each process now is working on m squared by t elements. Right? And then subsequently, right, I can take these p local sums and then add them up together serially. That's only going to take me p amount of time. Therefore, in this way of parallelizing, I have also tried to parallelize this part, making sure that the necessary synchronization is done in the last step. You can do the math to give you a performance which is closer to p, which is what you really wanted it to, because this p is going to be significantly smaller compared to n squared. Right? And therefore, this will give you a performance of p. So when you parallelize your program, always make sure that the sequential part is reduced as much as possible. That is the basic principle that you have to understand in parallelization. Right? I can possibly close my lecture at this point in time. Right? That's the one big takeaway message that you have. Okay. Now let's move on to the steps involved in parallelization. Right? I will try to define this somewhat formally, but then again, some of these steps can be combined together and do it in whatever way that you are talking. So just see what are the steps that are involved. Right? Before I do that, let me just give you a few definitions. I'm going to use the word task to mean some part of the computation. Right? So in my computations, I can identify maybe taking this block of a matrix as a computation that I do as one. But I can take this submatrix and then call that computation that I have to perform. Right? That's essentially what I mean by that. My task can be coarse grained or my task can be fine grained. When I say fine grained, very small. When I say coarse grained, then there's no notion of what is fine and what is coarse. Single element could be fine grained. A group of elements, maybe a handful of them, 10, 15, 20, whatever number, could be fine grained. Anything bigger than that, depending on the state of the problem, could be coarse grained. Okay, let's not really worry too much about it. I'm going to group these tasks together into what are called processes. Again, processes can be closer to a coarse grained granularity, right? These processes are the ones that are actually going to perform the computations that are described in those tasks. Right? I have grouped these tasks together into processes, and these processes are the ones that are going to perform the task. These processes may need to communicate with other processes, may need to synchronize with other processes in order to get that task. Because if these processes are independent, they perform computations without interacting with each other, and you are not really solving the problem of one problem which has to be solved together. Right? Some interaction may be required, and that interaction is required. Right? That communication or synchronization has to be required. One can again talk about process and threads. Right? There are some subtle differences here. But for this lecture, we will actually try to treat these two things as somewhat equivalent to each other. But when I talk about OpenMP, I'm going to talk about there are many threads. I'm not going to talk about there are many threads. There might be many threads, what I'm going to say. But ideally or technically, right, when we say process has a single address space. And when I say threads, multiple threads together can possibly share one address space. Let's find a distinction, but for the talk, let's not worry too much about. Okay. I'm going to use these two words somewhat interchangeably. One to mean slightly higher level of granularity, and the other to mean lower level of granularity. Okay. So, when you want to parallelize an application, what you need to do is that first you need to identify what are the one series of computation can be done in, right? This includes the computation, data access, input, output, and so on and so on. Like for example, when we talked about this matrix computations where I'm trying to update value of each element of the matrix, this could, let's say, this possibly squaring the right? I want to make A of I is equal to A of I multiplied by A of I. This computation is independent of any other computations that would happen in the array. Therefore, all of this can be done in parallel. So identifying this is essentially what we call as first step, decomposing them into smaller tasks that can be executed independently. Right? And then the second step is basically, okay, before I go to the second step, I'll say, how do you do this partition? This partitioning can be done in two possible ways. One is what is called as the domain decomposition, and the other one is what is called as the task decomposition. I'll talk about these two things, giving you specific examples. Right? But then after you do this decomposition into smaller tasks, you can actually go ahead and map these smaller tasks itself or themselves to the underlying architecture. But then because these are very fine-grained granular tasks, right, you may incur a large amount of communication and synchronization overhead on that. So what you do is that you group some of these fine-grained tasks into coarser grained tasks. Then you can ask the question, can I do this in one step? Why do I need to do it in two steps? Why do I divide it in finer grain and then combine them into four? Go ahead and do it. There's no modern POS tool that you can't do. Doing it this way helps you to identify all possible parallel computations and give you many possible ways of grouping them. That's the reason. Okay. Of course, once you have grouped them in terms of processes, right, or threads, then you need to worry about how do I manage data access between them? How do I manage the interaction? What are the examples of things? Right? How do I make sure that together they compute the correct? Right? Process is what we are going to call as orchestration. It's basically doing the communication between the processes if it is a distributed memory architecture, or if it's a shared memory architecture and a shared memory programming model, so it makes sure that these shared variables are updated in a correct way. Right? Part of it is a third. The fourth aspect which I have not listed here, right, is the aspect that pertains to how do I map these processes to individual nodes, or most of the time in parallel system, you may not have a lot of handle to do this. Right? The system or the operating environment itself will map your processes to the underlying processors or nodes. And that's probably the most efficient way in which you can use it. Unless you are an expert user who knows, oh, I need these two things to be together, or I need these two things to be closer to each other. In which case, you can actually define the mapping. But that comes with some cost, additional effort, as well as some system performance and so on. Let's not get into that step of right mapping here. Okay. Again, those steps are now depicted in the form of a figure. You take your computations, divide it into fine-grained tasks, group these fine-grained tasks into different processes, identify what should be the interaction between these processes, right? And those interactions need to be specified as a part of your parallel program. And of course, you do this to the underlying operating environment, which maps it to the physical processors on which they are going to be executed, or the nodes on which they are going to be executed. The first two steps, dividing this in terms of the fine-grained tasks and then grouping these things in terms of processes, they are independent of the underlying architecture. Right? You can just do the same way, whether it's a shared memory architecture or shared memory programming model. It is a good interpretation. Whereas this interaction that we talk about is specific to the model on which you are working on. Because if it's a shared memory model, then you have to have a quick set.
The arrows between P0, P3, P2, P1, and the lines between the processes themselves, do they mean anything?
They probably do not mean anything as long as there is some form of communication that's possible. It just could be a mesh, and you may be communicating to P3 may be communicating to P0 through this link. Okay, so again, going back to this point that the orchestration has to depend on the underlying programming model and the architecture. Like if it's a SAD memory programming model, then you have these variables, and when you want to add them, you put the appropriate block acquire, release, and so on and so on. Right? So that's essentially what it is. So distributed memory programming model, then you will explicitly send the data from this process to or receive the data from another node. Right? So this step is programming model architecture, right? Whereas these steps are not. Okay, so let me give you this example of how do I divide my task, right? How do I divide my computation into tasks? Right? As I said, it could be either called task decomposition or it could be called domain decomposition. Right? In the case of task decomposition, I look at my big task and then divide it in terms of multiple tasks. And then say that first I need to compute some task A, then I can fork 3 different tasks which can work in parallel, B, C, and D. B in turn might force additional tasks E and F, which need to synchronize or I need to do a join. Similarly, I have to wait for C and D to complete before I could do H. So I divide my computations in terms of these tasks and then express. Right? How do I do that? By understanding what my computation is all about. Right? And again, it requires some synchronization here because I need to join because G can only execute after both E and F have completed execution. Similarly, H can execute only after G, C, and D have completed that execution. So those are called synchronization points. Right? There is a joint synchronization that we are talking about. This is task decomposition. Right? So there is typically a fork join kind of a model, and just a barrier is essentially synchronization of all tasks. Join is essentially a group of. So one is more generalization. Okay, now let's look at what is domain decomposition. Today you use domain decomposition in most of the places. Let's again take out the example of a grid, right, where we want to square each element of, right, or square or do some addition, scalar, vector addition, whatever it is, right? For each of these elements which are independent of each other. Right? Because these are independent of each other, my decomposition can be at the level of each element. Right? The computation to be performed on each element can be independent, and node could be my. If I define my task to be that way in domain decomposition, then I have square tasks, which may be too many to manage. Therefore, I can group them together in terms of groups of rows or groups of columns, whatever I like. Okay? So that could be my problem. If I have, let's say, 4 processors, I can group them in terms of 4 blocks, right? And then assign each one of these blocks to this block. Correct? I could have actually group them, right, into more number of processes. For example, let's say that I could have grouped, assume that this is a huge array, right? Let's say 2048 by 2048. We could have grouped them, let's say, into 32, right, processes. And I have only 8 processors or 8 nodes. So that is fine. Right, I have 8 processes. Some of these processes are going to be mapped to the same node possibility. Right, there are some advantages. We'll talk about that line if you have time. Okay, that could be. Yeah. So don't think that the number of processors that you have, the number of processes that you want need to be equal. Need not out. Right, there are cases where you actually create more processes and do things. Right? We'll talk about those things perhaps during the interaction. Okay, so this is domain decomposition where you look at your data and decompose them in terms of what operations need to be performed on that data. And based on that you do, and this is essentially what is called domain decomposition. So your program can consist of both task decomposition and domain decomposition. It may not have to be one or the other. Some parts of the program could be domain decomposition, some parts of the program are these. Right? Task decomposition. Languages like OpenMP allows you to have some part of your code to be domain decomposed, some part of your code to be task decomposed. Awesome. Okay. So you need, if you want. Okay. So as I said, once you have divided them in terms of individual tasks, right, you can group them together, right, and then get what are called processes. And when you group them together, you have to make sure that you balance the workload, right, because each of these processes is going to be assigned to one of the processors, one of the nodes on which it is going to be executed. And in some sense, if you have them more or less well balanced, then the time by which they will end would be smaller, right? Otherwise, one process will complete it fast and then it will, if it has very little work and it will be. Whereas the other process is busy, right, doing things. So when you divide the work and then give it, you have to make sure that they are balanced. But sometimes you may not be able to do it all by yourself because computation being performed in different rows of the matrix could be different depending on kind of computation that you perform. Then what you need is that you need some kind of dynamic load balancing scheme. And that is where you create more number of processes than the number of processors and let the system handle the load balancing by itself rather than you trying to do. Because if you are trying to do, you can only do to the extent that you understand. Right? And sometimes certain computations which are performed in one row could be much more expensive than certain other computations. Some other. So you could do, I'm going to talk briefly talk about this dynamic load balancing at some point in time. And this is what you need to copy. Okay? Going this low but okay, again. Static versus dynamic assignments, we talked about it. Okay. So again, these are different ways of doing this assignment, grouping, have blocks of rows grouped together. They have individual rows which are being assigned to different processes. Or I have what is called block cyclic, where I have blocks of rows, again blocks of rows, again blocks of rows. Or I can do any possible mapping. Okay. Orchestration essentially talks about how do these processes interact with each other. Right? And if you have a shared address space model, then these processes will have some part of the address space which is shared across all of these processes, and they can directly access those variables. But some synchronization could be required. I'll explain that a little bit. Okay. And if there are different tasks, then you may also need something called yes. But if you have the notion of distributed memory, then there is no notion of a shared address space for data to be explicitly sent or received or sent and received. Okay. In the case of shared address space, one needs to remember that some part of the address could be shared, of the data or could be local to that particular process. Right, and every process may have its own local. Okay, so that's all about the parallelization essentials. Okay, we will see that some of these ideas actually come into play when we talk about OpenMP or when we talk about. Okay, so I'll just skip all of these definitions about OpenMP. OpenMP basically open specification of multiprocessing, supports the shared memory address. Right? OpenMP 4.5 or 4.3, right? They also support data parallel models. We'll talk about that. And essentially, what it contains is that it contains a set of compiler directives and some runtime libraries and environment data. These are the three things that are there to kind of support what is called the OpenMP program. Okay. And the very interesting or the very nice idea about OpenMP is that you can parallelize your program incrementally. That means that you can take your serial programs, look at one part of the program which you think is taking most of the time, try to parallelize only that part and leave the other part as it is. And you do that by including what are called WAS, right, compiler directives, like OpenMP directives. Right, and then you can take the same program and run it on your serial machine also, even after you have included the pragmas. So pragmas will simply be right. So that's the nice thing. You can incrementally parallelize your application. Right. OpenMP is vast. Nobody can do it in one lecture of 1.5 hours or one course of, let's say, one full semester possibly. Right. So I'm going to do it in 15 minutes. I'm going to only touch a very few important aspects of that, and then tell you you can go and read more about it. That's all I'm going to do. Okay, just to give you an idea of how OpenMP works, underneath we have the hardware, which is some kind of a shared memory system or some support for shared memory abstraction, right? And then on top of it, we have the operating system and support for shared memory, and we have a set of design libraries. Which is all available from the system. You don't have to worry, right? And then this is the OpenMP layer that we talk about. It has a set of directives or pragmas that we will introduce, and a set of OpenMP libraries that it supports. For example, to implement synchronization, barrier, so on and so forth, and a set of environment variables. We'll give you some examples of these. Right? Part is basically the OpenMP layer, and the application is specified using these OpenMP right primitives and variables, and that's essentially your application programmer. Right? So this is the layer of OpenMP. You compile your program with the OpenMP flags and so on and so forth. The environment included, the libraries included, and so on. Your hands-on session, maybe somebody will do that. I'm not going to get into those details. Okay. So OpenMP is essentially a fork join model, something similar to what we call as the task decomposition model. Right? But it also supports domain decomposition. I'll tell you how that happens. Right? So essentially what happens is that when you execute an OpenMP program, it starts with what is called a master thread. And whenever there is a parallel section, it essentially executes things in parallel in what are called as worker threads. Then again, at the end of the parallel section, there is a join. And then again, the master thread executes. Again, you may have fourth operation, multiple tasks to plan, and then joining. And these are the parallel regions in which things are getting. The parallel regions could either be task decomposition, where you can specify individual tasks, right? And they can be executed in parallel. Or it can be a domain decomposed task where you say that, look, I have this big array and I want to perform this on several elements of this array and I want to use n number of threads. Then that array is divided in some way, either like we saw, right? Block cyclic or cyclic, whatever way you want. There are ways of specifying how big the chunk should be, whether you want dynamic assignment, static assignment, everything can be specified in terms of optional threads. Right? And therefore, you can actually do domain decomposition as well in OpenMP. I'll come to all of them. I'm just trying to say these are incredible. Okay. Now, they said OpenMP is a shared memory programming model. So it supports the notion of a shared memory.
Yes, only threads do the parts of the code, while the master thread is it doesn't.
The master thread also executes, as you can see, this blue line. Right, is also executing one of the tasks. So, because if the master is also participating in the computation, right? Okay. The color coded it, I didn't say it explicitly. Okay, so again, coming back to the shared memory model, right? Many of the variables that are there in the program are shared variables. That means that any thread or any process can they all this single copy of that variable, right? We can also declare some variables as private variables, which means that each of these threads will have its own copy of that value, and only they will have access to that value. And on these private variables, those threads can go ahead and do any modification that they want because others are not going to see it, and others are not going to touch it. When you do modification to the shared variables, it will be seen by the other threads. And if two of them are trying to update them at the same time, there has to be some synchronization that is required. Okay, so unintended sharing of these shared variables with uncontrolled way of sharing them might cause a problem. Why do I say that? Let's take a small example. Assume that this variable X is a shared variable. Two of these processes are trying to increment in values. Assume initially the value was 0. Right? What do you expect the values to be printed here? 1025, 1525, 2525, all of them is fine. But what if it prints 1050? That's possible. Right? Because these two threads can run in parallel. would read the value of x is equal to 0 incremented. This will also read the value of x to be initially 0 incremented. One of them will write first, the other one will write later, and therefore they will end up writing and then, right? That's possible just because you allowed these two threads to access this variable x in any way that you want. You didn't impose any condition. So this is what is called a data race. Right? To prevent a data race, what you need to make sure is that you need to make sure that when you do updates to shared variables, they are done in what are called critical sections or atomic sections. Atomic section is basically one statement, critical section protein. The second, right? When you have to control this, look, I'm going to update my shared variables. And when I'm updating my shared variables, I don't want others to take the old value. Right? So you need to do the necessary synchronization. So whenever you do an update to a shared variable, right, as a programmer, you need to take care of that. If you don't take care, you could end up in values like 1050, 1010, so whatever value. Right. It's going to be one of them, but that is an unintended behavior. Because whenever you try to update a shared variable, you have to make sure that the synchronized way of practicing, right? There's some synchronization so that updates. Okay. All right. So let's go through some of the OpenMP concepts very quickly. I talked about the parallel regions. Okay, so here is an example. So this hash pragma OMP parallel essentially says that the next section of code is going to be executed. Right? Remember, the master thread executes up to here, and then the master threads along with the worker thread is going to execute this piece of code. Right? All of them are going to execute this piece of code. There is no division of work here. Everybody is going to execute the same part of computation, which may not be very interesting, but let's start with them. How many of them are going to execute this? It depends on how many threads that you have. Right? You can specify the number of threads using this OMP set. Okay. So, sorry, something got skipped. Okay. Yeah, the last got skipped. So, as I was saying, that if you don't have any division, then what's going to happen is that everybody is going to execute the same piece of code. So again, another example where each one of them is calling this function called foo, and then they are calling it with the respective ID because you can actually set the number of threads, and then each thread will get its ID by using this get number, right? And everybody is going to execute this function called foo, right? So, right. Pictorially, this is going to look like something like this, right? So you have the initial array declaration, and then the number of threads is set to 4. And there is a port that happens here, and all of them are executing it. Functions with different ID value, and then right, there is this print statement. But before this print statement, because this is a parallel section ends here. There is a synchronization. That synchronization is what is called barrier synchronization. This is what is called as an implicit barrier synchronization, right? And this variable A is a shared variable. Okay. Now, this is not very interesting. Every thread trying to do the same kind of computation, even perhaps with different IDs, not very exciting. Right? So how do I divide the work among these threads? Right? I can do domain decomposition, or I can do task decomposition. Right? So let's talk about domain decomposition. So let's say that I want to perform some operations here, y is equal to c of I plus c of I, and I want to now do these n parallel threads to be taking some part of the array and doing those additions, right? Because each of these iterations is independent of the other, can do them in, right? Supposing, let's say that I say that pragma OMP parallel, the next section is going to be parallel, and the way that I want to parallelize this is break this for loop, right? Using some static scheduling, which means that if I have 4 threads, then I want to divide this n in terms of first 1/4, second 1/4, third 1/4, and so on. Right? Then each one of those threads is essentially going to run or do the computation for 1/4 of the array. So I have parallelized and then work sharing. And in this case, the work sharing is done with domain decomposition because we are splitting the array into 1/4 each. I'm assuming that you would have set the number of threads to. Okay. If you have done it, then it's a time. Right? And after all of these threads compute the respective part of the computation, again, because the parallel session ends here, there is going to be a barrier synchronization. The barrier synchronization essentially means that you are not going to go past that statement until all the other threads or until all threads have completed this part of the work. That means that every thread is guaranteed to have completed the work that has been assigned to it. Right? And again, remember that this is static. I could have chosen this as dynamic. Okay, I could have chosen to specify the channel size, how much I want to go for each thread. I could have specified that. All of those things can be done using optional classes. Right? You will see more about it when you open up and read about OpenMP specifications. Alright? This is talk decomposition. I talk about OMP parallel and then OMP section. I talk about different computations. Now, if I have 3 threads, each one of these threads will execute one of them in parallel. And again, at the end, I will have synchronization, barrier synchronization. Right? By default, there is a synchronization. So I could do domain decomposition, I could do document. Yeah, go ahead.
You have, let's say, odd number of tasks and you have odd number of threads.
Odd number of tasks and even number of threads. Okay. So some of them is going to have 4. Right? For example, if I have 10 rows and I have 3 threads, right? Then one of the threads is going to have 4, the others will have 3. Right? If I have done chunk size is equal to something dynamic partition, then it will happen like each row going to, let's say, 1 thread, and then as soon as the thread finishes, it picks up the next one. Whoever finishes first will get one more row. Right? That's the sum.
Okay, so the thread which finishes first.
Exactly. Provided you did dynamic. Provided you did dynamic. If you statically divided it, you could have divided it as 4-3-3. Okay. You could have also divided it as 4-4-2. Nobody prevents you from doing it. You could have done anything you. Right? All possibilities are there. Okay. So again, many of the variables that you declare are shared. Again, I suggest that you look at the OpenMP, right? Manual to see which of them are shared. But you can also define certain variables to declare. When you say something is private, only that thread of that process, no other process can access. Shared variables, as we said earlier, how to be handled. Shared for anybody who's trying to do an update. If you don't synchronize, you cannot. Okay. Again, lots of definitions, lots of things to define. Right? Again, you can learn OpenMP incrementally. Whatever you want to understand first, do that, and then learn the other things. So, you ask what is private, what is loss private, so on and so forth. They can go on, right? Let's not spend time. Okay, so I already talked about synchronization. I talked about what are called critical sections and atomics. So we gave you an example of incrementing values, right? So again, the same problem. So in order to do this, you have to introduce what are called critical sections, right? So whenever you do an update to the shared variable, before you do an update, you have to make sure that it is updated only by one thread, constant thread, in a non-parallel section. So it is done. It is done in parallel, it is done in a critical section or what is called an atomic section. Okay. Again, there are lots of synchronization operations that are not going to. Just very quickly mention about the critical sections, and you define this. You see, abstract, OMP critical, and then give a name. Then there are ways by which critical section has been mutually exclusive and so on and so forth. Let's not get into this. But you can also similarly define what is called OMP atomic, which is for a single statement. So all that you do is that when you want to increment X, you put that increment inside the OMP atomic. Right? Therefore, it will be incremented by putting a lock around it. That means that even though many threads are working in parallel, the increment will happen only one thread at a time. One thread will read the value, increment it, and then write it. And then only the next threads are iterated. So let's just say that barrier we already covered, where all the talks be together. Okay. So here is an example which basically says and I have an OLP parallel section, and I do some computation, and then I do an update into a shared variable atomically, so by sharing an OLP atomic. Even though many threads will be doing these computations and they may be coming and updating this value, right? They can do this in parallel, but this update has to happen serially, one at a time, right? And then again, wait for that update to happen, and then I do the next part of the computation. Okay. One last thing about OpenNP. So something let's say that I want to get a dot product or something like that. Right? This is a computation. And again, this variable sum is a shared variable. If I say that there are n threads which are performing these operations in parallel, right? N is enough size of the array, right? If they all try to update this sum variable together, again you are going to have a problem. Right? So this is typically what is called a reduction. Right? OpenMP provides a reduction track. But let's see what that is. Okay, just directly go to the example and then tell you what. So you basically set the number of threads, and then you say hashtag OMP parallel for. It basically combines the OMP parallel and OMP for directives together, and it also says that this is a reduction operation. Right? So what this does is essentially the first example that I gave, creating P local sums and then adding these local sums together. Right? So even though this variable sum is a shared variable, because it is used in the reduction process, there are as many private variables as the number of threads that are assigned with each thread also have the same name as sums. Okay, but there is a private, and they do the private sum within themselves. And then subsequently, there is a piece of code that you don't see here, but when you compile it, that code gets added, where these private sums are added together to give you two global sums. That private sums are added together by one single thread or atomic. Right? So by using this reduction operation, you don't have to worry about the synchronization. You don't have to worry about many things, right? It automatically does it. Yeah. I have too many questions. Why don't you do one thing? This is the last thing in OpenMP. Just quickly introduce CUDA and then come back and then take your course. Right? I know. And again, these are additional things that allow you to set the number of threads, get the number of threads, do various things. Because OpenMP manual does. Very easy. So the last part, I'll at least spend 5-10 minutes on this, right? On CUDA. Again, Professor Ashad have introduced GPUs, right? And there's so many complications. So I'll try to make it as simple as possible. But there are too many things here. But before I go to GPUs, I'll very briefly talk about vectorization. Because many of you who are even using a single core know that these single core machines already have what are called the vector instructions, right? What is now called as the AVX instruction. Previously, it was called SSD, and then right after that, it was called that. What they essentially do is that they perform multiple operations. They perform actually the same operation on multiple parts of the data. For example, think that this is one variable, which is, let's say, either 128 bits or 256 bits long, one register, which is 128 bits or 256 bits long. Right? And each one of this part is, let's say, 32 bits. I can actually perform addition of these 232 bits and then store it. I can perform addition of these 232 bits and store it. So this is what is called as a vector instruction or the AVX instruction. Today's processors like your Intel processor or AMD processor and either AVS 256 or AVS or so on. Okay, that means that they can do, when I say 512, it is a 64-bit operations. Right? That is vector parallel. So very quickly. Okay, and the compilers allows you to take this code and then vectorize it. The vectorized code in assembly would look like this. Don't worry too much about it. Essentially says that load two data values, perform the operations on them, the multiply operations on them, and store the value back. And this will be done like if it's 128 bit and then you're talking about 32-bit operations, and 4 of them will be done in parallel. If it is 512 and then 32-bit, and 16 of them will be done in parallel. Right? The compiler takes care of it, particularly when the loop is a simple loop like this. And if the loop contains complex things like conditionals and other things, factorization will be required. Anyway, let's not worry about it. Let's just take the last 5 minutes for CUDA. Okay. So a CUDA program essentially looks something like this. Again, it's a C program with some part of CUDA code embedded into it. The C code is essentially the sequential code which is going to run on your CPU, right? And there is some part of the parallel code which is going to run on the GPU, which is what you call a kernel launch. The GPU has many SIMD codes and it has multiple what are called streaming multi, right? You'll worry about this SIMD code. Each of these SIMD codes is going to be executing one of these threads, right? And then when all of them complete their executions, right, you somehow synchronize and then come back to CPU, do again some serial code. And again, possibly you will launch another kernel where you will execute again. But this is how an open, this is how the CUDA code is going to look at. OpenCL is also something very similar. So that is in slide. Okay, now let's take a very simple example, right? I want to take x of I, multiply it by a scalar, and then add a element from the vector, and then store the result back in y of I. Right, again, by domain decomposition, I can think of each element to be a computation. Since we are talking about a data parallel programming model, I would actually like to stay at this finer grain granularity. Right, I don't want to now group them into processes. Right, take each one of these tasks, which is basically on a single element, and then say that that's my task. Right, I don't want to group anything more, and I want to now give it to this GPU, which has several thousands of CD cores, so that this fine grained parallelism could be exploited. Whereas when you talk about HPC systems where or a multi-core machines where you have only the order of 8, 16, 64 cores, or even if you talk about multiple nodes, 1024 nodes, and so on. Whereas here you have thousands of cores and you want to exploit the SIMD parallels, right? So what you do is essentially this. I just write what is the computation to be performed for each element. Don't worry about some of these things. They basically define what element on which I have to work, right? And then what is the computation that I have to do? I have to basically perform this computation and write the value with y of I. And what does this mean? This essentially says that, for example, right, I have a computations which is 64K, right? Elements, assuming 64 into 10 to the value. Okay, and each thread is essentially performing computation for one element. And I have grouped these threads in terms of 255 threads into one group, what is called a thread class, right? And now I have 64 such, right? 64 into 2, right? Now each thread is essentially performing this computation. There are 256 such threads. I'll show you there are 256 such threads in a thread block, and there are as many thread blocks as the number of elements divided by. Okay, so that's essentially what this program is saying. Now you can think of your SIMD code being executing each one of these threads. Again, Luca would have introduced this notion of a warp in that, right? So a warp is essentially a group of consecutive threads. 32 threads together is a warp that executes in a lockstep manner, and that's what is being indicated by each one of these things. Right? So if you have 255 threads, then it's amounting to 8 different warps. Right? There are multiple such warps which execute. Right? And these warps are multi-threaded. Right? They can switch context. Every cycle you can take instructions from a different warp and execute and so on. Right? Those things are possible. Okay. Just to quickly conclude, remember that we said that there is a serial port, there is a kernel launch, and then again there is a serial port. But then the CPU and GPU are two different devices. This is typically how you see them. There are these integrated CPU, GPU computers, but that's it. Okay, so if you see these things as discrete devices, then the CPU has its own memory and the GPU has its own memory. This is typically what is called as the device memory. So before you execute a kernel onto the CPU, a kernel on the GPU, you first need to make sure that the data which is available in the CPU memory is transferred to the GPU. Then you put the kernel to the GPU, and then that gets, in terms of thread blocks, it gets scheduled on this multiple streaming multiprocessors, and then it gets executed on the GPU. The values are finally available in the GPU memory, which you have to transfer it back to the CPU memory before you go to the next serial computation. Right? So putting all of those things together, right, this part of code will look like this. You do some CUDA malloc, then of course you do some copying of data, then you execute another kernel, then you copy back the values, and then do some CUDA. Right? I'm sorry that this is doing all of this in a very compressed one slide form, but I think that's all that time that I have. Okay. So with that, I will actually conclude my discussions on CUDA. As I said, I have only touched upon some very small aspects of OpenMP and CUDA. There is a lot more to learn. The current version of OpenMP is 5.x. It also supports some data parallel computations and so on. There is other things like method parallel. And of course, CUDA is current version is 12.x. There's some things called dynamic kernel invocations, CUDA graphs, and so on and so forth. A lot more to come. Right? I'll stop here, and if you allow, this was. So, Shiva, you would please start. So we take another 5 minutes of questions. Okay. Questions? Yeah.
So when we do when there's critical
sections.
so what if like the order of like thread one running first and it was running second and thread
Okay.
running.
So if you again take my example of adding 10 and 15, the order didn't matter. Correct? Whichever order I do, it is fine as long as I do it one after the other. So the critical section essentially allows you to do that. If you do want to have a specific order, then you have to somehow make sure that the other one cannot get the synchronization before the first one finishes. There is some ordering mechanism by which you can.
And so the also like
So again, you will use some kind of blocks directly, but make sure that one block is acquired in a particular order.
and like distributing the tasks and like distributing the data like this having shared memory support like is better for one and does that
Not really. Okay. It's not like domain decomposition is good for memory machines or block decomposition. Right. In fact, OpenMP recognizes that and allows both form of decomposition to happen. But in certain tasks, certain cases, and these tasks could be done in parallel. And you don't want to very much use block decomposition. For example, OpenMP allows you. You have another question here?
In the process, when we said that the work is distributed in a efficient manner, but somehow if one of the processes is taking longer, will the task which is left will it be redistributed among the process and to reduce the time? Because
Unless you have done some kind of a dynamics. Let me just give you an example. So let's say that I have divided my array into several sections, and I have given this piece of work to 10 probability. So let's be very honest. So I have divided my array into 100 parts, and I have 10 threads which are running, 10 processes which are running. I said that each one of you take this 10, that 10, that 10. If I do that, that's static assignment. The moment I do static assignment, I'm stuck. That's like saying that you complete grading of this assignment, he completes grading of that assignment. That person completes grading of that assignment. Then until you finish or everyone finishes, not done. Then I say that look, the stack of papers are here. You take one paper grade, put it back, to the next paper. So whoever who grades faster can actually do more. Therefore, together you can complete. That's dynamic assignment. Because I didn't tell you upfront which set of papers you're going to grade. As soon as you finish, maybe yours inherently slow, or maybe there is one paper which required a little bit more time to do things. Right? So that may take a little longer, and in the other time, there are processes which can actually work on that, actually do that work. So that is dynamic distribution. Okay. So OpenMP allows you to group your tasks dynamically. So that's why the dynamic class is explored.
it is already for a question, why not only have dynamic? Why there is a need for
Some cases you could actually do static also at a equal class. By default, it is static. And dynamic has some overhead cost in terms of assigning these tasks. Some additional. Yeah, you have.
Yeah. So, given some problem, what principles sort of dictate which would be a better programming model for that? Like, given
You are more going to say that okay, I have this machine. What is the programming model that I have? If you have a cluster with shared memory in it, then it's not be an MPI program with some parts of it exploiting the shared memory. It's more driven from that part. You should ask experts like Pratik who actually your answer that. Yeah, it's one last question. If there is one, yeah.
Question was for the programming and the connection between the hardware. So when you put some primer there, so it will go into the port and it will perform the parallel processes. But if there are like multiple cores and a separate thing as a GPU, how do we know that it's assigning tasks to multiple cores or it's going to GPU?
So for assigning task to GPU, you have to do it easy. They OpenMP 4.5, OpenMP for separate and mask. Yeah. So typically threads it's only assigned to threads. CPU cores.
So the program we saw, so that will be going
Not basically cores. And then within that thread you could actually have a kernel on OpenMP which you could and it allows I think maybe you have one for us.
Yeah, I just wanted to know, like, this is a growing tool. I'm sure the internet has a lot of good resources. Are there any that you could recommend for people who are more of users rather than?
So many of them are for users. They vary anywhere from a 3-hour tutorial to much longer one. I don't have anything specific as a recommendation, but I can look it up and then give you the link. For CUDA, the best resources from NVIDIA. Anything that you get from NVIDIA, people possibly the best of those. For OpenMP, I have seen some from Intel. I think Mason's one is a really good one. I don't remember the thing on top of my head, but I can get back to you. Yeah.
Thanks a lot.